Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.4.5 on inverse series. All right. So we're going to think about recursion, um, but using series. And here we start with an example, Towers of Hanoi. So this is a game where you have things stacked like this, and the idea is you can take things off and put rings in different places. But when we do that, we don't want to do it in any kind of way where we stack something on top of something else so we don't want to run into something like this. I'll just draw it out. We don't want to have, we don't want to stick something bigger on something smaller. Okay, that's against the rules. So we want interested to know how many steps it actually takes to move this somewhere else, like move it to the middle. So this is kind of a recursive picture actually of what's happening. What if we could just move the top part of the stack somewhere to another peg? That would be like the number of steps of solving the game if you had 3, right? How are we going to move things around between these two so that we finally get what we want, like this being over here? And in fact, if you want, you could just think of this as a single disk, maybe, and you move it to just a peg. So just think of this red block as a single peg, or a single disk. So you can move, but this disk is smaller than the blue one. So this disk moves to there, then you can move the blue to the middle, and then you can move that one on top of that. It's also a recursive idea because what if you just solve the problem for moving these 3 to there? That's like a whole number of steps just to get that piece to there. Then you move this to there, and then you just have to solve the problem again, moving this to here. And you can use that other peg over there. So the idea is kind of in the recursion, we get a nice, we can come up with a recursive formula. It'll be a recursive formula. And it's basically this: the number of steps to solve the problem for like for 4, what was it? It was 2 times the number of steps for 3, because we did this time here and then there again, plus 1 more move. Okay, so we get a nice recursion. To solve the puzzle, in fact, by inspection, we can actually, just by listing out the sequence elements, we could automatically even just guess this. 2 to the n minus 1. But nonetheless, that would be a nice formula for the number of ways. Let's actually work through another way of doing this using series. How can you come up with formulas? So we talked about how we can come up with formulas using matrix powers, but we can also do this using series. So let's get started and see what we can do. Okay, so if we can multiply, okay, so let's start with the recursion right here. We can multiply that recursive formula by x to the n. And then we get this. Now, why were we doing that? Remember when we were dealing with sequences before and relating them to polynomials in another section in this book? We were thinking about coefficients of something to a power. So what we're doing is we're setting us up for that. So we're going to be thinking about like a sequence with this is the in the nth position, and this and different things with the being in the nth position. And if we add up over the powers of n as we go from 1 to infinity, we have some series, and we can split the series up over this addition right here and get a sum of series, just like that. Now we can be clever here. What if we write f of x to be this, to represent a sequence of just the ANs going up? All right, so that's kind of nice, because then the coefficients in here would be what we want. Like the nth coefficient of f you know, associated with x to the n would be, if we could have come up with a formula for that, we'd be good. So maybe it'd be nice to write this as f of x. Now notice if we do that, let's just kind of think about what's happening here. We can rewrite this series as 2 times f of x. This guy right here, actually, it looks like a geometric series with a sum of 1 over 1 minus x, but it's missing in the first term. So if you write down the geometric series formula for this guy, and then just subtract off the first term, that would be equivalent to that series. So this guy is equal to that series, and this is equal to that series. Now, this one over here, let's see what that would be equal to. This is a lot like f of x, but we've shifted a little bit. In fact, it's like we have our power of n is 1 less than it should be with an plus 1. So it's like we divided all of our terms in f of x by x. But that's good and fine. But if we actually do f of x divided by x, the very first term won't even appear here. I mean, like, think about that. So like a1 x, so a1 x1 divided by x would be like a1. Well, the term a1 doesn't even happen here. So okay, so we're going to subtract out the extraneous part of the shift and note a1 x over x. But notice that a1 is 1. And how do we know that? The reader should verify that a1 is 1. So that was right there. Okay, so that's something for the reader to verify, that it only takes 1 move if you only have 1 disk, and that should be pretty clear. Okay. So if we try to write this series right here as this, that we'd have too much. So we take out what was extra, and then we have this nice equation going on. This is a -1, and you have a -1 on this side as well. Notice that this -1 and that -1 will cancel. So this really will look like this. So we have a nice equation with f of x this way. We can get the terms with f of x on one side, and multiply both sides by x. All right, so we multiply both sides by x. So this would be, and maybe I'll write up just the in-between step here. So if we multiply both sides by x, then we have f of x is equal to 2 f of x times x plus x over 1 minus x. Okay. And then we can subtract, then we can have f of x minus 2 f of x. Notice we can factor out f of x here. That's what we have there. 1 minus 2x is what's left, is equal to x over 1 minus x. Okay. So that's where we're at right now. What we're doing is we're trying to come up with a nice way of thinking about f of x. So we're solving for it. And notice when we do it, we get f of x is equal to a nice fraction here. Okay. So if we want to come up with a formula for the nth term of f of x, it's the same thing as coming up with that for this expressed as a power series, or as a series. So let's think about that for a minute. What we could do is we could use something called partial fraction decomposition, if we were in maybe like a Calc 2 class or something like that. But for us right now, let's do something else. Let's actually use matrix powers at this point. So we're going to actually do a mixture of series and matrix powers. How are we going to do that? Well, we'll see. Okay, so we're going to write this equation right here as, let's see, 1. So let's move this up here. So it's 1 minus x times 1 minus 2x times f of x is equal to x. Okay, so x is equal to that. All right. This is equality of 2. Okay. All right. So this is equality of 2 series. Because this is a series over here, even though it just has one term, this is infinitely many. But over here, most of the terms are 0, right? for n is greater than or equal to 2, the coefficient of x on the right is simply 0. So we can simply write, let's just write that this is equal to 0 for powers bigger than 2. Okay. So maybe we can just, kind of think about this series as being things with powers higher than 2. And we can just, okay, let's distribute this through and then actually divide by x squared. Okay, divide by x squared, that was the first power that we were actually looking at. We're still going to get a 0 over here, but looking at this, let's think about what this is. This is, what does this look like? F of x over x squared. It's kind of like what we've done is we've shifted, we're like taking our terms like this an plus, like think of like an plus 2. In f of x, the power would be, let's write that out. Okay. So we can kind of think about this a couple different ways. A term in f of x would be something like this, right? And if you divide by x squared, that would look like, the terms now would look like this. Then if you could write this as an plus 2 x to the n, if you like, just by shifting indices, but it means the same thing. This index here is 2 more than that one. Okay, so this gives us a nice way of, okay, so we can write this. So basically what we're doing is we're coming with another recursive formula. So he's had one recursive formula, then what we're doing is we're transferring it into another recursive formula where we can use matrix recursion on. The first one we couldn't really do matrix recursion on. Why was that? Let's see why we couldn't do it originally. We couldn't do it originally. No, because we had kind of like, we were adding by even a number over here. Wasn't even like, and then here we didn't have two things or whatever. So this is kind of a lot different than the Fibonacci case. And we couldn't really use the matrix right away. However, we just kind of turned it into a case when we could. So, and that's what we're getting right here. So this part right here, okay, we look at what the terms look like. We're just going to look at this equation, but we're going to equate and just look at the nth term. The nth term is always 0. All the terms are 0. So let's just look at everything that has x to the n in it. So something that has x to the n in it here would be this guy coming from here. Coming from here, it would actually be n plus 1 x to the n. That's because we're dividing by x. So the power of x will be 1 less than associated with the coefficient. So if you have an x to the n, it'll be an plus 1 there coming from that guy. And here it's just going to be like it is, just an associated with xn. So if you just look at coefficients of x to the n, this is what our equation is at each level. That is a recursive formula right there. All right, so there's a recursive formula, and we could use the idea of matrix powers, and doing it, we get a formula for a sub n using a power of a matrix. That this formula comes from the recursive formula right here. This is -2 and 3. That's what we're putting here, -2 and 3, where this is like a higher, like an plus 1. This is an. Okay, and there goes a 1 there. That just has to do with the shifting right here as we go. And looking at an, okay, now this is interesting. Why is it n minus 1? That's because we're starting with a1 instead of a0. That's a difference there. And there, a little description right there. Okay, so in order to compute an, we want a formula for this guy. We can take the determinant of that matrix, and we can mod out by that. Okay, so we're going to be modding out by this and using our technique here in solving for a and b by plugging different things in. We can, and we end up getting what a is. And so we get a formula for a, and we get a formula for b. And so we get a formula for a, we get a formula for b. And then right here, we can think about what the formula for an is. All right. Okay, so let's just look at this. So an would be this, right? And Okay, so that's our, so what we've just come up with. Okay, okay, so we're trying to find out this power. So we've just raised it to that. And we solve. So ax plus b, and that picks it out. Now an. So this looks the same, except, and we came up with a formula, but this must be a typo. Let's just take a look at this. A1 is 2. Oh, this is interesting. The typo perpetuated, it'll be fixed. Okay, so let's just imagine that right here, these are, this is A1 and A2. That's just a little typo there, but that's okay. All right, so if you're reading this, hopefully that's correct in your book. And we'll go along here. So that's A1 and A2, and that'll be, and that's also going to be, so just imagine that's A1 and A2. Okay, so this will pick out, okay, so we use this basic procedure that we had before, just remembering that this right here is what we just solved, the matrix that we just solved for to the n-1 power. And we put it in. It's funny, that was perpetuated right here, even though we used the values of A1 and 3. So we actually did it correctly, even though we miswrote it there. But we ended up getting 2 to the n-1. Okay. Wow. All right. That was a lot to think through. Is that even useful? Why didn't we just do it by inspection to begin with? Well, it gives some insight to how things can be done sometimes, and it's helpful to see things in multiple ways. Well, for one, let's think about the recursion right here. Remember how we had that U and the W? Well, so U and W, remember how I kind of talked about how to get our matrix quickly? You can just get it from those guys. And the determinant, and you can even just look at the determinant right here. You actually see U and W in the determinant as well. It's kind of interesting to see these guys in here in the sequence and in the polynomial right here that we were looking at in that determinant. Okay, and also to be thinking about this formula here, see how it kind of simplified? It was just like the B and A. In fact, that's what we got in the Fibonacci sequence as well. It's just BA dot that. That's really all it is. It's just B times A sub 0 plus A times A1, where it's AX plus B would be what we'd get from this A. So that's kind of useful to kind of see that pattern so you can more quickly do these types of problems. Okay, so here's another example. Suppose you have this recursion. Now notice in this recursion, we also have this extra term here, like a 3 to the n. So it'll be kind of like the last one because we can't really use a matrix right away, but we can change it so we can use a matrix via series. So we can multiply everything by x to the n. And then, okay, so then, and we're going to be thinking, so kind of spearheading to where we're going, thinking of a f of x here associated with this guy right here. This guy will be like difference of, so this is 1 less than that, so it's kind of like f of x divided by x. So we kind of think f of x divided by x. Then over here, this is like a power series because it's like 3 to the n, x to the n, so like 3x to the n. So you can almost think of it as just 1 over 1 minus 3x. All right, so we now, okay, adding up all, now remember we had to be careful about eliminating some terms. Okay, so look like adding terms to have us at smallest power of x to the 0. Okay, we're lucky in this case. Okay, is the only term with the smaller power. Okay, actually, yes, in our actual recursion, if you put in, yeah, even, okay, I'll let you look at that case because A0 in our case is actually equal to 0. That was given in the problem. Okay, 0 was equal to 0, so that was the only issue that we really had to throw out in f of x over x. So this was actually equal. We didn't have to throw out anything there. And this guy, right here. Okay, so that means we can go all the way down to 0. Okay, so looks like we're pretty good because we're going all the way down to 0. So really there's nothing to throw out here. And we're also looking at, sometimes we can just look at terms above a certain place anyhow when we're making equalities, but nonetheless, okay, we get the basic idea. We have f of x over x, that over that, and that, and then do the same basic. So we do the same basic thing. We get f of x times something is equal to x. And so we can just look at powers that are higher here and then divide out by x squared everywhere. And we get a new recurrence relation because we have f of x's here. So we have like the coefficients an and different shifts going on. And we can relate them at each power. We get something like this. We change a recurrence to that. We can use matrix ideas. So this is a 6 and a 1 here to write down the matrix here. And here, since we're starting at a0, we're good. Here we can use an n. And we can find out what a is. So a to the n is. We found out what a and b are. So we can kind of do the simplified version. We know what a and b are, so we can go b times a0 plus a times a1, which is exactly what we had here in the simplified version quickly, because that's kind of what it's turning out to look like as we moved along. Okay, and so we ended up getting it. Notice in the actual determinant here, let's see the 6 one here and the -1, -6 here, how it's reversed. We could even just jump to the determinant here from, you can even just jump to the determinant here from this recursion, right? So you can just jump from this step to this step even, just from that observation, and then go ahead with these calculations and get them. Okay, so we've been finding a recursive sequence for something like this, like x over a polynomial. And why is that? Well, let's think about this. Like, we have x over a polynomial, then so right here, like f of x itself, if we solve for it, it's like x over a polynomial, because we're looking at the coefficients of f of x. That gives us the sequence that we're looking at. So we have like x over a polynomial. That's what we've been looking at. What if we just look for like 1 over a polynomial? In fact, that would give us a nice way of even coming up with a formula for an inverse, series inverse, so of a polynomial itself. So like if we want to invert a polynomial, let's come up with a way of doing that and knowing what the series looks like. Okay, so we have f of x is equal to that. So in particular, for powers bigger than 1, it's, it gets 0. And then if you divide everything by x squared, and okay, for n is greater than or equal to -1, we can rearrange this into a recursion. Okay, and let's see, but let's start off this recursive formula with a0. So let's figure out what a0 is. And the way we did that is we realized f of 0 is equal to the constant term. So we just plug in 0 to get the constant term, which is a0. Okay, that's fine. So we get 1. All right. So we know a1 is equal to that. Okay. Great. So we get a0 and a5. Okay, so now we can go. So we have a0 and a5. Okay, now we can go for it and find a to the n, which we compute what a to the n is right here, by finding a and b. And using that, we use this form right here. So notice that we're skipping now to this step here. So a1 plus b times a0. And we put in what we got for a and b, and we come up with a nice formula. So this is a nice formula for the coefficient of x to the n. in the inverse series. So writing this out, this looks like, okay, so the terms look like 3 to the n plus 1 minus 2 to the n plus 1, x to the n. We have a series as n goes from, okay, so this is what the inverse series would look like as n goes from 0 to infinity. We just computed or figured out what f of x is equal to, which is equal to 1 over the original matrix that we were, or the original polynomial that we were trying to invert, which, remembering what it was right. It was this guy right here, 6x squared minus 5x plus 1. Notice that 6x squared plus 5x plus 1 is different than this polynomial right here. The coefficients are kind of backwards from one to the other. But nonetheless, we were able to figure that out. Now, there's another way of doing that. If you think about partial fraction decomposition, geometric series, you might notice exercise to the reader, whoever's interested, just kind of maybe noting that this is like coefficients in this series, and this is like coefficients in this series subtracted together. If you could figure out that this was equal to this, which is a partial fraction decomposition idea usually taught in a Calculus 2 class. Okay, so that concludes this this little subsection and the whole section here of 6.4. Thanks for watching.